is on inverters, okay? So single phase and three phase inverters for photovoltaic and motor drive applications. So essentially, I'll deliver 3 lectures, okay, on this topic. So this is the first lecture, and the lectures are not really, well, I'd not say evenly divided into 3 lectures, because some of the slides, I have probably less amount of slide in this lecture. So what I'll do, after finishing this lecture, I'll probably do a few slides from the next lecture as well. But in these 3 lectures, we'll look at the single phase, mainly the single phase inverter, how you analyze them, how you design them, how you control them, and also briefly I'll also show you how to analyze the 3 phase inverters, okay? So first, an introductory slide. Inverters, they are the most important power converters, I would say, for practical application, okay? And it is becoming more and more important for just because of the reason that we are having more and more renewable energy system, okay? You know that because of the climate change and everything, we are moving away from the fossil fuel. Just quickly check if it's recording. Yeah. Right. And with the new renewable energy system, for example, you have solar PV, okay? And the solar PV, because the way solar PV works, because of the physics of solar PV panel, the voltage or the current it generates, it's a DC voltage and DC current, okay? Now, if you look around, wherever you have the electrical connection using the power grid, they are all AC, isn't it? All the sockets in here, they are AC, the lights, you know, projector, everything's run from an AC system. So you are generating a DC voltage, DC current, but everywhere else is in AC. So of course you have to convert the DC voltage or DC current to an AC voltage and AC current, right? For general usage. So you need a DC to AC conversion, which is done by the inverter. So it's not just the solar PV. For example, in electric vehicle, you have batteries. The batteries are DC again, but the motor, which runs the wheel, you know, which actually will drive the vehicle from A to B, that's an AC motor. And so you need a DC to AC converter. Another example is that you might hear a lot fuel cell. Okay, fuel cell is another type of renewable energy system where you use hydrogen to generate electricity. That fuel cell is also a DC system. Now, if you want to, again, if you want to use it, if you want to make a versatile use of fuel cell, you have to have a converter, which is a DC to AC converter. So as you can see, now because of the new renewable energies, in different applications, we need this inverter even more than before. So this is a huge topic, which will have, but we will only focus on the key concepts, and we will only look at these 2 applications, photovoltaics and the motor drive. And we will start our analysis from our half-bridge building block, okay? So that I know I've delivered probably last 4 or 5 lectures just on half-bridges. So hopefully you should have a nice background in terms of how do you analyze the half-bridge, what's the characteristics, how do you, do the modulation, etc., etc. So we'll use that knowledge as a base to analyze the inverter application, okay, or inverter operation. So as I just explained, photovoltaics and motor drives, they are 2 very different applications. However, we'll see that basic principles, such as the converter circuit, the control, they have a lot of similarities. We'll first focus on the single-phase photovoltaic converter, and then we'll introduce the 3-phase inverter, and that will be pretty much at the end of the 3rd lecture. Okay. So as you can see here, I'm showing you the 2 schematics, okay, circuit schematics. This one is a single-phase inverter. It's using PV panel as an input. It works like a, as I said, it's generate DC power. So there will be a DC voltage in here. And whenever we want to connect this to our grid, we need to convert this DC to AC, and we use what we call it a full bridge inverter circuit or a full bridge circuit. And then we connect the DC to AC, we convert the DC to AC, which goes to the grid, okay? Why we call it a full bridge? You remember this first half, we call it a half bridge, okay? Now basically what we did, we connect two half bridges. When you add two half, then you get something full, so just we call it a full bridge, okay? However, you will see in our analysis, we can actually use just a single phase, a half bridge circuit to do the inverter, to work as an inverter, okay? But again, in the second lecture, you will see the full bridge circuit is actually better than the half bridge circuit when you want to convert the DC to AC. But it is possible to use just a half bridge circuit to convert the DC to AC, okay? And this application can be a simple rooftop application. You'll see in many households you have solar PVs on top of the roof, okay? And it could be even this kind of big farms. So there are lots of megawatt level solar PV farms where you can, so it's just the bigger in scale, okay? On the solar, on top of the rooftop, you might have 3, 4, maximum 10 PV panels connected together. But there could be hundreds of them or thousands of them connected together to generate megawatt level power, okay? And the second application, as I mentioned, is this three-phase inverter. So as you can see, we have, in this case, 1, 2, 3 half bridges, okay? So to create a three-phase inverter, what you need to do, basically you connect 3 half bridges in parallel. And then by using modulation techniques, you can convert the DC voltage, which is in here, which comes from this battery stack, okay, or battery pack, and that converts the DC to AC voltage needed for the motor, okay? And that AC voltage generated at the output of this three-phase inverter, there will be a phase shift, okay? So phase is a standard, three-phase system. So the three voltages will have 120-degree phase shift, okay? Which you can do by using the proper modulation technique for the three-phase bridge, which is utilized in this inverter. And this is just a simple, photo of the, I think this is a racing motor. I don't know if you know, University of Nottingham used to have a racing team. So this is motorcycle from that racing team, and I think it was champion a couple of times in the Isle of Man TT. So, and it was a lot of the things are developed in the University of Nottingham, power electronics machine and control group, PMC group, such as the motor, power electronics, and other things. Right. So as we saw that both of the converter converts DC source and inject it into an AC source. It could be a grid or it could be electrical motor. And if we want to represent it with block diagrams, simple 3 blocks, we have the DC source, we have the inverter, and we have the AC system. Okay. And now in this scenario, the power can flow in both directions. So the power can flow from the DC to AC system and also AC to DC system. How it will flow in both systems, we'll see in after a few slides. Okay. In terms of equivalent circuit, what we can represent, especially these two systems, the inverter and the AC system, we can represent it by using a very simple, this is sometimes called a transmission line model as well. And we will basically, in this lecture, we will explain how you can utilize this simple equivalent circuit where you have basically 2 AC sources. VAC is the AC voltage of the grid. V inverter is the AC voltage generated by the inverter. And then we can just put a simple L, which is a filter. And this simple circuit can model this system, where your DC source is connected with an AC system via an inverter. So why do we want to look at the photovoltaic applications? As I mentioned first at the beginning, that with the renewable energies, we need to get rid of the fossil fuels. Traditional electricity generation, they are usually based on, nowadays a lot of gas-fired power plant. There is still a couple of coal-fired power plant. There are nuclear, but we really want to move away from all these fossil fuel-based power plants because they emit a lot of CO2. So we are moving towards wind energies, so using offshore wind turbines, and also another important renewable energy source is the photovoltaic system. So in the UK, if we look at, there is a significant growth in the PV market. Okay, you might think UK is cloudy and it's raining all the time, but still there is a lot of PV potential. Okay, for example, probably even higher potential in the south because it's slightly more sunnier. In last year, in 2021, so yeah, 2 years back, 730 megawatt of PV power was added, and 50% of them are rooftop PV. Okay, and of course, with the now that the price of the electricity has gone up, so PV panels, if you put a PV on top of the houses, it's looking more and more economical nowadays. So that's pushing the PV growth as well. So, which means, as I think I briefly mentioned as well, the PV can be, installation can be domestic, which has the rooftop PV, which can be few kilowatt, and they are usually low voltage. So it's basically the voltage output is suitable to connect it with the 240 volt AC system, which is the low voltage distribution system. Whereas the large PV farms, they are, could be tens of kilowatt and could be up to megawatt, and they operate in medium voltage. So the voltage output from those large PV farms could be, few kVs to tens of kVs. Okay. So in total, we have over 1 million PV installations in the UK, and as you can see, it's almost 15 gigawatt of installed power at present. And in terms of big solar farms, there are more than 1,000 solar farms in the UK. The largest one is 72 megawatt, but there is a planned very large solar farm which is 350 megawatt, but it has not been commissioned yet. Right. So it doesn't matter what voltage or what power the PV is generating. As I mentioned, the PV is giving you a DC power. So if you want to connect it with the grid, if you want to use it for your appliances, you have to convert it to AC. So you need an inverter, okay, which interface the PV system with the AC power grid. And domestic installations are usually single phase, and if you go to high power, then you move to 3-phase. So we'll start with our single phase inverter. There are many topologies you will see to design this single phase inverter, but you will look at this half bridge building block based inverter. So as I said, mainly we'll look at the full bridge inverter where you connect two half bridges together. And yeah, for system architecture there are several options, but yeah, we'll just look at the basic system architecture as well. So in terms of PV characteristics, so on the left hand side, this is what we call the IV characteristics of a PV panel. Okay, so current and voltage characteristics. So if you think this is the symbol for the PV panel, and if you look at the VPV, that's the voltage across the terminal of the PV panel, and IPV, which is the current out of the panel. And the PV module, whether it's one panel or hundreds of panels, if you look at all those panels, in single panel you have several cells connected in series and parallel. Okay, so if you want more voltage out of the PV panel, what will you do? Will you connect the cells in series or in parallel? Any idea? Yeah, series, right. So because every cell will give you a certain voltage. So if you want more voltage, you connect cells in series. If you want more current, you connect cells in parallel. Same thing with the panels. Once I give you a panel which gives you a certain voltage and certain current, if you want more voltage for your home, what you will do? You will connect a lot of panels in series. If you want more current, then you put them in parallel. That's the standard. But whatever you do at the end of the day, it will give you a certain voltage and current. And this is the IV characteristics. And on the right hand side, we see the voltage versus power. So PV is generating DC, so it almost works like a DC source. But if you look at the IV characteristics, it's not really like it's not working like a traditional DC source. So if you look at this section of the current is constant, right? So it's working almost like a constant current source, okay? And after this point, you see the current with the increase of voltage, the current is falling, okay? So at that point, you have, of course, a current and voltage relationship. So, but in a normal DC power supply, the power supplies that you used in the lab, you remember the load is actually controls the current, right? When depending on what load you connect with the power supply, whether after a DC-DC converter or something, if the load is needs more current, you will get the more current out of the power supplies. Now, so basically what I'm trying to say here, between the PV and standard DC power supply, they are not really equivalent, okay? Now, this current in here, what we call IPV, like this current in here, the maximum current, we call it short circuit, okay? So basically, this current, what we call it, ISC, okay, short circuit current, and this voltage in here, we call it open circuit voltage. Okay. So any PV panel, if you open up the data sheet, it will give you this IV characteristics plot, and from that you can calculate the short circuit current and open circuit voltage. Why short circuit current? If you look at here, at this point the voltage is 0. Okay. So when the voltage will become 0? If I short it here, if I short the PV terminal, of course the terminal voltage is 0, right? So that's at that point we have the maximum current out of the PV. That's why it calls the short circuit current. Why the second point is open circuit voltage? Again, if I make sure, sorry, this is like an open, when the circuit is open, the current is 0, but then you get the maximum voltage out of the PV, okay? But in applications, of course, with the PV panel, you have some sort of converter, it could be an inverter, then of course you will have, loads connected to it, okay? So there will be, as long as you put a, load with the PV panel, of course, the PV, there will be certain voltage, and depending on the voltage, there will be a certain current. So if the voltage in here, the current will be in here. If the terminal voltage in here, the current will be in here, okay? At which point, which current you will get for a specific voltage of the PV, you can get it from this IV characteristics, okay? Now, if we convert this IV characteristics into the power, so on the y-axis, we have the voltage times current. You will see the power is actually changing, right? On the right-hand side, if I just erase this, if you look at here, the power is changing, okay? And at this point, for this voltage, we have the maximum power, okay? So for a PV panel, there is a certain voltage which gives you the maximum power from the PV. So it's of course natural. We want to operate in that voltage, right? Because in that voltage, which is in this case at this point in here, we get the maximum out of the PV. So that's why what we connect after this PV is, before the inverter, we actually connect a DC-DC converter, okay? DC to DC. And that DC-DC converter, first of all, generates a certain voltage in here and also makes sure my VPV always stays at this point, okay? VMPPT, okay? Sometimes this converter is also called maximum power point tracker, MPPT, okay? And the whole purpose of this DC-DC is to generate a fixed output voltage and also to make sure your terminal voltage across the PV matches this fixed power point. Now, another problem is that this IV characteristics that we are seeing is actually, it's not fixed. It changes. It changes with irradiation. It changes with temperature. So we'll see. I'll just quickly draw what will happen with irradiation. Irradiation, it will look like this. When you change the irradiation, So basically, this short circuit current goes down as the irradiation. So, irradiation means sun intensity of the sun, how sunny is it. If it goes down, the short circuit current goes down. And which means, if you look at this is my maximum power point. This is my maximum power point, this is my maximum power. So that maximum power point is also shifting, okay? So for that reason, you need this DC-DC converter to track that maximum power point. And that's why we call it maximum power point tracker, MPPT. So we just saw it, what I've just explained in here. So when you have solar radiation decreases, this power curve is also changing, and you have basically, as you can see, two voltages. So when if the power based on the irradiation of the based on the basically whether the day, how sunny is the day is, you might have to operate in V2 or V1, and that you can get by using the DC-DC converter. Okay. And also there are other architectures. So there are also other architecture where you can do direct connection of the PV with the inverter, okay? But we'll not discuss them because they get really complex. So you can use certain inverter topologies where you can use the inverter as MPPT. So you can use some sort of modulation strategies to also track the maximum power point without using the DC-DC converter. But because we are trying to simplify the analysis as much as possible, so we are just assuming we are not consider this direct connection. So the structure we are considering here, we have basically the PV, okay, here, which is it will generate a variable DC, and that DC voltage will, what voltage we want in this PV will be controlled by this DC-DC converter. As I said, it will also try to fix the output of the DC-DC converter to a constant voltage. So from the inverter perspective, what we'll see a DC fixed voltage, because we'll consider there is already a DC-DC converter which is fixing my VDC. So from the inverter analysis, it becomes simplified. You have a fixed DC voltage, then you have the inverter, then which will connect it to the AC system, which is the grid. Okay. And yes, and also I'm not going any detail on the DC-DC converter and how you control it to get the maximum power out of PV. So again, some of them, well, the DC-DC converter analysis, control modeling, I teach it in 4th year. If you're doing an MH, you will probably, if you select that module, choose that module 4118, that's where I go in more details on the DC-DC converter analysis and small signal modeling and control. Right, okay, so, but DC-DC converter, after this, this is the inverter we want to basically analyze, because, without the inverter, we cannot send the power from the PV to the AC system. And yeah, how can we do this task? Okay, so as I said, simplified analysis, we have a DC power supply, okay, which is the output of our DC-DC converter. We have the inverter and we have the AC system. Now, what we'll assume in here, we were assuming the power can flow in both directions. So power can flow from DC to AC system and AC to DC, okay? So the inverter is like a bidirectional system. Now, my question here, based on your knowledge about PV, do you think the PV panel can accept power? So if I think that there is only PV after, as I said, there could be a DC-DC converter in here, and there I have the PV. If I don't have anything else, that means from the AC, if the inverter is bidirectional, I'm trying to push power into PV. Is that feasible? No. Because PV system is a unidirectional system, okay? There is no regeneration. If you put energy back to the EV, if you put electricity back, it will not emit light, okay? So if you put light on it, then it will generate electricity. So, but the reason we want this to be bidirectional is because there is also a battery storage, okay? So what basically you'll see in the next slide, we also have a battery. We also have a battery in the system, okay? So at this point, because we're looking at this DC link, right? So not only in a normal system, we have the PV, also we have a battery storage. So what's the application of battery storage? Very simple. In many applications, because for example, especially in households where people are working during the day, then you don't really need that much electricity during the day. But during the day, when you have a lot of sunshine, so you have electricity generation, but no consumption. So what do? If you have a battery, you can store the energy, right? So when you go back home at night or in the evening, when your demand is higher, when you start cooking stuff and turning on the heating and everything, so the energy which is being stored throughout the day into the battery can be used throughout the day. Okay, so throughout the night or throughout the evening. So normally, what we need to have is this. Without this battery storage, we cannot achieve that. So now that we have a battery, of course, the batteries you can charge the battery and you can discharge the battery. So if the inverter power is bidirectional, which means when the power flows from the AC system to this DC link, the power can go to the battery as well. So you can use the battery to store the energy from the grid as well, because that's also another application. At night, if you have like a economy 7 tariff, at night your electricity tariff is low, significantly lower than the day tariff. So what you can do also, at night you can use the inverter to store energy in the battery at low cost, and also when the tariff goes up, you can utilize that energy. So there are different advantages of using a battery in this PV system, and for that we want the inverter not only put power from the PV system to the AC system, or if we think about this DC link, not only we want the power to go from this DC link to the AC, but also we want the power back to the DC link as well. Okay, so we can achieve that by making sure the inverter is bidirectional. Okay. Okay. Yeah, I think that's just what I just explained. Yeah, and in this module, we'll always assume that bidirectional inverters for simplicity, and another reason is because it's the most common one. And another thing is that if inverter is bidirectional, it doesn't mean that it will always try to push power back from the AC system to the DC link. It will depend again anyway. How do you control it? Okay, it's a fully controllable bidirectional system. Okay. So you can control it to work as an unidirectional as well. So if there is any system where you don't have any battery, you can use still the same circuit, but you just control it to flow the power from the PV system to the grid. Okay. But in the rest of the analysis in this module, we'll consider bidirectional operation of the inverter. So what we have seen with that example that I gave with the battery energy storage, said not only we basically with the battery energy storage, we want to absorb power from the AC grid and store it. So from the AC system, if we look at, because the power, again, the power is flowing through the AC system and going out of the AC system, from the AC system perspective as well, the power is bidirectional. Okay, so the grid is not only supplying power in this system, like when you charge your laptops, batteries, everything. Not in most of the cases, what we are seeing, the grid supplies power to the load. But in this system, because of the PV, the grid is also accepting power from the PV system or from the battery system. So how do we model this simplified system? As this is the equivalent circuit. So as you can see, we have two blocks in here. The first, on the left hand side, we have this blue dotted block where you have the DC supply and the inverter. On the right hand side, we have only the AC system. First, AC system. Let's discuss how can we model this inverter and DC source. So inverter and DC source, as I said, we can use half-bridge building block to construct the inverter, and the half-bridge block is like a voltage source converter, VSC. And the voltage source converter, you saw some of the, in our earlier lectures, the voltage source converter is nothing but a voltage source. When you do an equivalent circuit, when you did the equivalent circuit of the half bridge, what did we get? We get like a voltage source, right? You remember there was a low frequency voltage source plus a high frequency voltage source. High frequency came from the switching, and we used an inductor to filter out the high frequency voltage source. So essentially, because it's a VSC, we can use a voltage source, which is shown in here, because it's the difference between previous voltage sources with this is that this voltage source is AC instead of DC, because we want to generate an AC output from the voltage source converter. So we have the voltage source, we have, as I said, a filter, inductor, but for the AC grid, normally the way you represent the AC system, again with an AC voltage source, which if it's not, it's basically 240 volt RMS. So this is an AC signal plus an inductor, which is LAC, and this inductor represents, the AC system. You have transformers, you have transmission line. All this, of course, will create an inductance. So that all the different inductances we can lump together into one inductance, which is LAC. Okay. So basically, our inverter is considered. Well, our inverter, we are representing it with a voltage source, VINV, and the AC system is being represented by an AC voltage source plus an inductor, LAC. Okay. So, okay, and also we have the additional inductor L, which, of course, we looked at in the last couple of slides. We need this inductor to filter out the high frequency ripple from the voltage source converter. Whenever you have a voltage source converter, you have to filter out the high frequency ripple. Now this is the simplest filter. You remember when we designed our inductor or calculated our inductor, we mentioned that L with just one inductor is just the simplest one. But you can have, instead of L, you can have an LC filter, you can have an LCL filter, but we will not go through those filters, but because simple L can do the job in this, in our case. Another approximation what we will make is that we will assume this LAC, so all the inductances associated with transmission line transformers, we will neglect it. We will assume the grid is ideal, so LAC, we will basically assume LAC is equal to 0. So the system or the equivalent system will be simplified to be like this. So you have the inverter voltage, which are generating from the inverter circuit or half bridge circuit. We have the AC voltage from the grid, and it's being coupled by this L, which is the filter inductor. And you can see the AC voltage will look like this. Okay, so it's a 240 volt RMS, 50 hertz AC signal. So any idea what will be this value in here? What will be the peak value? If the RMS is 240, what will be the peak? 240 times root 2, right? So if you multiply the RMS with the root 2, that will give you the peak of the voltage. Okay. So yeah, these are very standard. Probably you know it from your A levels. But some of the very basic things will be useful in these lectures, and also the example questions. If when you want to answer some of the example questions or understand the analysis in here, very basic things, as you'll see, some of the very basic trigonometry, very basic phasor analysis will also be needed in this lecture. Okay. So that we in this to control this system, what we can do, we can control this V inverter, right? In this circuit, if we design a specific value for L to filter out the harmonics, this VAC is fixed, right? Because the grid voltage is always fixed. Normally, it will not vary unless you change your country, of course. Okay. Any idea? If you go to US, what will be that voltage? 60. 60 is the frequency, 60 hertz. What will be the voltage, RMS voltage? It's 120, okay? In the US, it's different. Instead of 240 volt, you'll get 120 volt. And yes, you're absolutely right. The frequency, instead of 50 hertz, you will have 60 hertz. So, but, you know, in all over Europe, and majority of the world, basically, you have this 240 volt RMS and 50 hertz grid system. So if VAC is fixed and L is fixed by our design of, you know, of course, I will show some calculation how to design L or which value of L you should use there. Now, how the controlling of the power we can do by controlling the V inverter, and which we can control. You remember the half bridge circuit, because V inverter is the output of the half bridge circuit, and half bridge circuit we can really, the reason we use half bridge circuit is to generate a controllable output voltage, right? And if you can remember, we do it by using the modulation strategy, okay, which you will see. Now, why do we need this inductor? As we mentioned, of course, we need it for filtering, but also between these two power sources, one is the V inverter, another is the V AC, we need something in between to, you know, to separate the two voltages. Because if you don't have something, it's like a short circuit, you know, you can't really connect them. So if we look at the current, simple in phasor formula, now as soon as I put this sign on top of a variable, whether it's the current or a voltage, you know this is a phasor, okay? The phasor means it's not a fixed value. It's a complex number, okay? A plus J times B, something like this, okay? Or like, you know, P at an angle phi. So any phasor you can represent it with a complex number or with a, you know, with a magnitude and an angle. Now, if I write in phasors, the current phasor will be simple. We have the two voltage sources. So the difference between the voltage sources is V inverter minus VAC. And if you divide it by impedance of the system in between the two voltage sources, that will give us the current. Now, let's assume what else we can put in as impedance instead of L. So if I put Z as a resistor, what will happen? Any resistor, of course, it will have I square R loss. Okay, so you can't really put a big resistor between your inverter and the AC source. Okay, that will create a lot of I square R loss, which will reduce the efficiency. But you will have some inductance. Okay, don't get me wrong. Because your inverter needs to be connected to the grid or to the appliance with some cable, and the cable will have some resistance anyway, but that resistance is significantly small compared to the inductance that we will connect for filtering. Can we use Z as a capacitor? It will not do the filtering job, right? Because you remember capacitor, it's 1 over J omega C, right? So ZC, the capacitor impedance is 1 over J omega C, which means when omega increases, if the frequency is increasing, the ZC goes down. Okay, so basically, if the impedance decreases at high frequency, it will not be able to filter out the high frequency component. We want an impedance there which can filter out, which will give a very large impedance to the high frequency signals of this V inverter. So capacitor is not possible, so we used an inductor, and we already saw in the half bridge analysis how this inductor can filter out the high frequency components. Now let's look at some of the trigonometric analysis. First, we look at the only reason we will do this analysis first using trigonometric calculation to calculate the real power and reactive power in the system. Again, real power, reactive power, you should probably studied them in year 1 definitely, and so it's just a revision of the year 1 system. But I'll go through all the basics anyway. Okay, so let's assume this VAC, which is our grid voltage. Of course, it's a sinusoidal signal, so we assume the signal to be this V sine omega t, which is shown in this green sinusoidal waveform. As you can see, it's omega t, so the phase angle is 0. Now the current that's flowing into the grid according to this direction, we assume it to be I sine omega t plus phi. So depending on the value of phi, the current can be considered lagging or leading. Okay, so if phi is less than 0, then we can assume the current is lagging. As you can see, lagging means the current is starting from 0 a little bit later than when voltage is starting. So voltage is starting from 0 there, and current is starting from 0 there. Leading means current is starting from 0 a bit earlier. So current is actually starting from 0 if we extend it from here, but the voltage is starting from 0 there. Okay, so we have two generic expression, the voltage expression and a current expression. Now the power is, if you multiply voltage and current, that will give you the power. Okay. By the way, if I try to prove some of your knowledge from your year 1, so out of these two figures, which one is inductive current? So, you know, the top one, and between the top and bottom figure, do you know, can you tell me which one is inductive and which one you get it for capacitive current? So if your load is inductive, which one of them is actually showing that characteristic? Any idea? First one, yes. So absolutely, because in an inductive current, the inductive current is actually lagging the voltage. In an inductor, current lags the voltage. So that's why the first one is what you'll see, that when the current is basically inductive, if you think of it as a load current. Anyway, so if we multiply voltage and current together, we get this power equation, and just, you know, V peak, I peak, sine omega t plus phi. And now this is like we can use a trigonometric formula. Sine A plus B is equal to sine A, I don't know, cos B plus cos A sine B, which you show, I'm showing here. So this second term, I can write it in this way. And if you look at here, there is one term. Just assume all the terms with phi, because phi is fixed, it's a fixed value. Just assume when the term with omega t, that's where we need to focus in terms of which one is in phase or out of phase. Because we have sine omega t for the first term, which means the first term is basically in phase with the voltage. The second term is cos omega t. So basically, the current is quadrature with the voltage in the second term. So now, if you multiply this, first Vi sine omega t with this whole equation, we get the two terms again here, which is I'm showing it in blue and red. The first term, you have the cos phi sine omega t, sine omega t. Sine omega t means sine square omega t. Sine square omega t means 1 minus cos 2 omega t divided by 2. And sine omega t cos omega t, we can replace it with this equation. So just basic trigonometric formula. And at the end of it, we come up with, again, two parts. If you look at the blue part, it's, of course, as I said, this is fixed. Then you have this cosine term, and you have, again, for the red part, this is like a fixed value. Then you have the sinusoidal term. So if we plot them, it will look like for a specific phi, which is minus pi by 3, and the current is 50 and RMS, voltage is 240 volt RMS. So the first figure, this is showing my voltage, this is my voltage, this is my current, and when you multiply both of them, this is power, okay? And on the last figure, we are actually separating the two terms here. The blue one is shown by this blue figure, the red one shown by the red figure. Okay, so if we look at the last figure, the blue and red, one of them, as you can see, the average is 0. Which one? Can you tell me? So the last figure, you have two waveforms. The red one, yes. So if you take the red one, you see the average is 0, right? Negative part and positive part, they are equal. Negative part and the positive part is equal. Again, can you remember which part of the power in an instantaneous power, the average is 0? What do we call that power? Reactive power. Okay. For if you have instantaneous power is part of, is combined of two power. One is the real power, another is the reactive power. Real power is something that's actually being used. For example, it's being converted. If you connect a load, if you connect a resistor, that's the real power, means that power is converted into heat, or if you put a light, that power is converted into light. Okay. Reactive power is the power that's not being converted. Basically, it's an oscillatory power because you have inductor capacitor in the system. Okay. Reactive power is like an oscillatory power. So in some cycle, power goes from, if there is an inductive term, power goes from that inductive term to the load, and in some cycles, part of the cycle, power flows back. So average power is 0. So again, by look at this, if you look at the red second term, as I said, the one I circled, that's a fixed value, and this is like a sine omega t or sine theta. The average of any sine cosine is 0, right? Any sinusoidal signal, this is a sinusoidal signal, right? Or if you do sine minus sine, cosine minus sine, average is always 0. So that means this average will become 0. But second term, 1 minus 2 cos omega t, which is basically was sinus square omega t, in that case, because it's a sinus square function, the average will not be 0. And that you can see from the blue curve. Okay. So if I erase this, again, if you carefully look at the blue curve, it's always, as you can see, it's always positive. So there will be an average value. And that average value will, what we call is the AC, is called the AC real power. Okay. So, and same thing, if you look at the power, the total, when we plot the, P of t, it will also have an average of value. Okay. And that average value will be equal to the average value of this blue line, and which is the real power in the system. So instantaneous power equation is this. We have two parts, the blue part and the red part. The blue part is, as I said, if we take the average, that will give us the real power, which is V peak, I peak divided by 2 cos phi, and the peak of the, basically peak of this red line, that will give us the reactive power, which is V peak I peak divided by, so this is the term which is our reactive power. Okay. We can also convert it into RMS. This is same thing, because if you can write it square root of 2 times square root of 2, right? Which means V peak divided by square root of 2 means VRMS. I peak divided by square root of 2 means IRMS cos phi. Okay. It should look familiar, right? Power is VRMS times IRMS times cos phi, and cos phi is basically the power factor. Same for the Q, reactive power, it's VRMS, IRMS sin phi, and the reason it's negative, again, if it's because if you look at our phi is negative, right? So if you put the value of phi in here, QSC will be positive. When current is when you have basically inductive current, then you assume the reactive power is positive. When you have capacitive current, then you basically the standard is the Q will be negative. So when phi is a positive angle, the Q will be a negative value. Okay, so let's assume our power factor um, uh, uh, angle is 0. So phi is equal to 0. When the phi is equal to 0, cos 0 degree is 1, but sine 0 degree means 0. So which means when the power factor PF basically phi is equal to 0 means power factor is equal to 1, then it means that there is no reactive power in the system. The only power in the system is real power, which you can see in here. As you can see, basically this is voltage and this is current, and they are in phase, so they are crossing the 0 always at the same point, so they are absolutely in phase, and which means this is the case when you have power injected from the inverter. So the power is flowing from the inverter to AC system. And when the current is in antiphase, as you can see in the second figure, now the current is sort of in antiphase with the voltage, then still there is no reactive power in the system, but the real power is flowing in opposite direction from the grid to the inverter. Okay? So now we have looked at all this analysis based on the trigonometry, which is, we have done all this analysis based on time domain, and we've looked at all the waveforms, which are all time domain waveforms. For calculating equations for real power and reactive power, and which voltage you need for a specific real power, which voltage or angle you need for a specific power flow, or which voltage magnitude you need for reactive power, we need to use phasors, because using phasors you can derive formulas which you can use as a design equations. Okay, so so using the phasors, we'll be able to calculate what we need as V inverter from the inverter circuit. So we go to the phasor domain. As I mentioned a bit earlier, any sinusoidal signal, we can represent it with a phasor. And just as if this is the peak of the sinusoid, so if we divide it by square root of 2, that will give us the RMS, which is here, and the angle, the phase angle, we can use e to the power j delta. So and this is basically the phasor representation of this sinusoidal signal. Okay, any sinusoidal signal you can convert it to a phasor number. And again, as I mentioned, the phasor can be represented as a magnitude and an angle, plus also in the form of A plus JB in this formula as well, with the real part and the imaginary part. Okay, and which basically you can write from this equation as well. E to the power j delta is basically cos delta plus j sine delta. Okay, so if you use this formula, you can go from this representation of the phasor to this representation of the phasor. Is it clear? Any questions so far? Now let's look at the phasor calculation. Okay, so in phasor, what we can write VAC, because the angle for the VAC is 0 degree, no phase shift, so we can write the VAC phasor as VAC. And the current, as we saw, the current is, there is an angle and the magnitude, so I can write the current phasor at I e to the power j phi, which is, if I write the equation for e to the power j phi, it goes to I cos phi plus j sin phi. And the apparent power, now, again going back to first year, the apparent power is, in phasor equation, to calculate the apparent power, you need the voltage phasor times the current phasor, but the current phasor needs to be a conjugate number. So that's why you can see this star at the, in the apparent power equation. So the conjugate of I means this phi e to the power j phi will become minus j phi. Okay. Again, going back to the basics, if there is a complex number a plus jb, the conjugate of that is a minus jb, and in phasor if it's, I e to the power j phi as shown in here, the conjugate will be I e to the power minus j phi, and which gives us the equation for the apparent power, which has two terms, as you can see, VAC, ISC cos of minus phi, which means cos of phi. So we have the one part which is the AC power, AC real power, and another part which is the AC reactive power. Okay, so we can write two equations, PAC and QAC, as you can see in here. Now from this equation, if you square, basically if I want to derive the first equation for I, what you do is square them. PAC square plus QAC square is equal to VAC square I square, right? Because cos square plus sin square is equal to 1, isn't it? Cos square phi plus sin square phi, that's basically 1, which means to calculate I, we get the VAC square on the left hand side, square root it, we get the value of I. And finally, if you divide the two equations, QAC divided by PAC, that gives you a tan phi, and from that you get the formula for phi. Okay, so it means if you know the real power you want in the system, if you know the reactive power you want in system, and if you know what is your AC voltage, which is normally, as I said, is fixed, because the AC system, the grid voltage is always fixed around 240 volt RMS. You can calculate what's the current. You can calculate because we want to calculate this, right? So we want to calculate I and also e to the power j phi. So we calculate the magnitude I by using the first equation, let's say equation 1, and by using the second equation we can calculate the angle. Okay, so just by using this two simple formula we can calculate the required current in our PV inverter system for a specific real power, for a specific reactive power. Okay, yeah, so also once we get the current, what we can do, we can calculate the voltage we need for the inverter. Simple equation, because current is V inverter minus VAC divided by Z. So if from that we can calculate the V inverter is IZ plus VAC. Again, the VAC second term is always normally fixed. If you know the Z, which is in our case will be an inductor, so if we know the value of L, Z is also we know, and we have just calculated the I phasor. So if you from this equation we can calculate V inverter, basically what we want to generate at the output of our full bridge circuit. So this analysis can also be done using phasor diagram, which is shown in here. So if we just first thing we need to draw is this VAC. So if you want to draw this phasor diagram, first thing you need to draw is the VAC, because VAC angle is 0. Okay, so you can draw this line. I'm just redrawing on top of it. Once you draw the VAC, next thing you need to draw is the IAC. Okay, and that's because we know already that IAC will have an angle. What do we call this angle? Phi. Yeah, so as you can see the current has an angle phi, and because we are assuming Z is equal to L, because it's an inductive load, basically an inductive load in the system, so the current will definitely be lagging. Okay, so once we get the two waveforms, the two phasor VAC and IAC, which are linked by this angle phi, then what we can draw is this VL. Okay, because for an inductor the voltage and current phasors are perpendicular to each other. Remember, the current and voltage phasors are perpendicular to each other. So if we know the IAC phasor in here, we can just draw a perpendicular line which will give us the VL phasor. And if you look at this phasor diagram with the VL, if we add the VAC, which is shown in here, so this is my VAC, then we move this line in here. So we draw the VL, and if you look, this is just a vector addition. If you add this vector with this vector, you get this vector, which is basically V inverter. Okay, and that again, the V inverter will have a magnitude, and also will have an angle gamma. So same analysis we can do based on the phasor diagram as well. So how how do you do the control of this system? Basically, first step is to define the active and reactive power we want to exchange with the AC grid, the P and Q. And based on the P and Q, we can calculate the current needed for the desired power flow. Okay. So basically, going back to this equation, so we need, if you look at here, we need the P and Q, and VAC is fixed. We can calculate the current I. So that's my second step. And the third step, once you know the current magnitude and current angle, by looking at the circuit, whether you use the phasor diagram or simple circuit analysis, you will calculate the voltage, the inverter voltage that you need to drive that current. And you can use your control circuit to generate that specific inverter voltage from your half bridge inverter or full bridge inverter. Okay, so we will in terms of step, we do the 1 and 2 first, then the current reference. After second step, it will generate a current reference which will go to your closed loop controller, and the closed loop controller will make sure you generate a certain amount of voltage out of the half bridge or full bridge inverter to achieve that power flow in the system. Okay. And in terms of design, one of the things we need to design is the inductor L, which is the filter in here, L. And we'll see in the next lecture how we can design L by looking at the worst case scenario for the system. Okay. Now if you want to derive a generic formula for the P and Q, the real power and reactive power, again we can use some phasor calculation. Going back to our earlier equation, S is equal to apparent power is VAC times I's conjugate of I phasor, which gives us this. Now the same equation we can rewrite in conjugate. So I think the second step I'm not showing, but the second step will be VAC conjugate times I. So if we take the conjugate of the whole equation, let's say this is equation 1, if we take the conjugate of that, it will be PAC minus JQAC. Okay. So from that we get the I phasor basically. So P minus JQ divided by VAC. So this is basically one expression of I, and another expression of I by looking at this circuit is if you divide that, because the current is flowing from V inverter to VAC, the voltage difference between voltage difference across Z is V inverter minus VAC. If you divide it by Z, which is the Ohm's law, you get the I. So these two I phasor expressions, they are equal. So we have this equation, and then we just next thing is just a simple algebraic calculation. We multiply this VAC goes to the right hand side, which gives us this formula. And if you just these two terms, we can, VAC is the AC voltage of the grid, so there is no angle, so VAC is just a normal number, VAC, but V inverter will have a magnitude and an angle, as you can see in here, and Z is equal to, because it's an L, it's an inductor, so the impedance is j omega L. And if we do the multiplication, we can see there is a real term. So if we look at, if the j and j cancelled out, so this term, there is no complex number with this. So there is a real term in this, and there is an imaginary term. Okay. So the real part, of course, the real part PAC is the real power. So this is the expression for the real power. The imaginary term, which is the Q, so that's an expression for the reactive power. Again, simple algebraic calculation will give you the expression of real power and imaginary power, which is the real power and reactive power. One simple approximation we did is that, as you can see here, we have a sine delta term. So when the sine gamma is very small, okay. You know, basically the angle for the inverter is the angle is quite small, which is from the phasor, this angle. If this angle is very small, which means sine of gamma is equal to gamma and cos of gamma is equal to 1, because cos of 0 degree is equal to 1, isn't it? So it's like cos 0 degree, which means 1. Okay, so if we put that simplification, sine gamma in this sine gamma term can be replaced with gamma, and this cos gamma term can be replaced with 1, okay, which is shown in here. So basically, by doing this approximation, we get some generic expression for active power and reactive power. Now the active power exchange with the grid is controlled by the, as you can see, this angle, phase gamma. Okay, so the gamma is actually controlling the active power, and the reactive power is controlled by the amplitude of the inverter voltage. So this V inverter, VA and V, is controlling the active reactive power, because rest of the things are pretty much fixed. If you look at the second term, reactive power term, L is fixed, VAC is fixed. So the only thing you can control is the magnitude, V inverter. So that will control your reactive power. And once you know the magnitude V inverter, if you change the gamma, that will control your real power. Okay, let's have a look at this simple video, which, as you can see here, it's a Plex simulation. You have two voltage sources. One is the inverter AC voltage generated by the inverter circuit, and VAC is the basically the grid voltage. In between you have the inductor, and in Plex, you know, Plex doesn't really like pure inductive or pure capacitive load. You have to always add a small resistor to make sure the simulation is can go through without any error. So that's why we put a small resistor. So we'll see how, if initially what will happen, we'll put these two voltages exactly same. Okay, so this is 240 volt RMS, angle 0 degree. We'll also put as 240 volt RMS, angle 0 degree, and you will see the current is actually 0. And then we will change this inverter voltage. First we will change the magnitude of this inverter voltage, and then we'll change the phase of the inverter voltage and see how the current changes for this for when you change the V inverter. So let's just try to run this. I hope it will run. It was running in my computer. Okay. As you can see, it's 240 volt, square root of 2. That's the amplitude, 50 hertz. So when both of them have the same amplitude, same phase, okay, then if we run the simulation now, the red waveform is the voltage, okay? The red is the voltage, the green waveform is the current. As you can see, because you have the exact same voltage, same magnitude, same phase, no current flowing in the circuit, okay? Now, in this step, I'm changing the magnitude. As you can see, it's now 1.5 times. So we haven't changed the phase, we've just changed the magnitude of the inverter voltage. See what happens if we run the simulation. Now we can see some current flowing in the circuit, okay? But if you look at the phase of the current is actually just 90 degrees shifted. The voltage, if you look at the phase, the voltage and current phase, the phase shift is 90 degrees. That means there is no real power in here. All the power in here is basically reactive power. It's like a pure inductive load, okay? Because we haven't changed the phase, we just changed the magnitude. You understand it? Because we just, in this step, we just changed the magnitude of the V inverter, didn't change the phase. You remember last time when we derived the equations, when you change the magnitude of V inverter, it will change the reactive power flow, but it will not change the real power flow or active power flow. Now, in this case, I just make sure the two magnitudes are equal again, so the current is 0. So I have reverted back to the initial condition. Next simulation, we'll see what will happen if you change the phase. You see the phase, now the phase changed to pi divided by 10. So we have a phase angle. So amplitude is fixed, but we have created a phase shift between the V inverter and VAC. Now you can see the current, which is in phase with the voltage, which means you have real power in the system, but no reactive power. Okay, because as you remember, the angle, the phase shift controls the real power. The magnitude, now the phase shift is negative. You'll see the real power will change. Okay, now the current is there, but it's in antiphase. So still there is only real power, no reactive power, but the power flow is now in opposite direction. Okay, because we make the phase shift negative, so that the power is flowing from the AC to VAC to V inverter. Right, okay, so I think that's the end of first part. In the second part, we'll look at some of the more half bridge and full bridge inverter circuit, and also in the next couple of lectures we'll see the rest of the stuff. So we'll have a 5 minutes break now, and then I'll start again. Thank you. Right, let's start again. Okay, so as I mentioned, we have those 3 lectures, but this is sort of part of my second lecture, where we can look at how we can use this part. I'll not go through all of the lecture, just a little bit of this lecture. And we'll just look at how we can use a half bridge circuit, not a full bridge circuit, just a half bridge circuit, how we can use the half bridge circuit to work as an inverter. Okay, so we're looking at this, just a reminder, we're looking at the single phase example, and we said we can use half bridge, and we saw that the simple inverter system, a simple inverter system connected with an AC grid, we can represent it with this equivalent circuit, which V inverter is the voltage generated by the inverter. And we looked at some of the equations which will give us the magnitude of the voltage that we need from the inverter and the angle of the voltage that we need from the inverter. We can calculate it based on the power, what's the power, real power, reactive power we want to inject into the grid or want to get from the grid. From that we can actually estimate what will be the V inverter, this V inverter peak, and also what will be the value of this angle gamma. Okay. Now a reminder circuit of the half bridge control. You remember this is the half bridge circuit, and we controlled it with a PWM modulator. Again, what's the purpose of the modulator? The PWM modulator works like works like a system modulation, where basically you try to embed a low frequency system, low frequency signal within a high frequency signal. So the low frequency signal is the signal that you want at the output of the half bridge, which is this VBN in this case. Just a reminder, in this case we are assuming the negative of the DC rail as the reference. Okay, we have the DC link voltage, 2 devices S1 and S2, and VBN we are considering the output of the half bridge. And so from this analysis, what we can do in terms of getting like a sinusoidal signal, which you can show, I'm showing in this figure. So we have this triangular waveform, PWM carrier, which is a triangular waveform, which is the CT, and if we use the modulation signal, which is sinusoidal, we can also get a sinusoidal output, okay? Because we remember the VBN average is basically the MT, the modulation signal, times VDC. And this is how you sort of create like the block diagram for the modulator. So whatever voltage you want at the output, you use it as an input at this block at here, and then you divide it by VDC, which gives you the MT, and you compare the MT with a CT, which is the triangular waveform, which gives the GBT, the gate signals for the two devices, S1 and S2. Okay, and another thing, because the input DC link is has a fixed voltage VDC, we remember the output can only be between 0 or VDC, because the output is like a pulsating output, where you have, if you take the average of this pulsating output, you have a low frequency signal, which is shown by this variable DC source, and you have the high frequency signal, which comes from the carrier because of the switching of the two devices. And basically, we don't want these high frequency signals. That's why we use an inductor to filter out the high frequency component of the output. Okay. Now, from this, the main message I want to give here, with this circuit, we can only get positive voltages at the output of the VBN, because it goes from 0 to VDC. Basically, if you use this circuit, you can get a sinusoidal signal, but only positive voltages. Will that be good enough for our inverter? No, because inverter, we saw it's an AC voltage which goes from positive and negative value. Because in this circuit, we cannot achieve that. Basically, we cannot, although we can generate a sinusoidal shape waveform, we cannot really use it as an inverter. So what we can do, we just do a very simple change, which is basically splitting the DC link and put a ground or reference in the midpoint. And we saw in earlier lectures, these two circuits are equivalent. All we are doing in here, instead of looking at the reference, instead of taking reference at this point, negative DC link, we are taking the reference point as the mid of the DC link. So if we look at the mid of the DC link, now if you look at the voltage between this point and this point, if you say this is our output voltage, VBO, then basically we can write the equation VBN minus VDC, because again, quickly, if I write down the, if you do like a KVL equation in this loop, which gives minus VDC by 2, and VBO, you see this is on the right hand side is plus, so it will be minus VBO plus and VBN. So just by writing a KVL equation, we get this formula, which gives us the VBO, the expression of VBO, if you take it to the right hand side, is VBN minus VDC by 2. Now, remember I just said in the first slide, VBN can be between 0 and VDC, right? So assume if VBN is greater than VDC by 2, so from this equation, what will be the VBO? If the first part, VBN, is greater than VDC by 2, VBO will be positive, right? Okay, if the first term VBN is greater than VDC by 2, VBO is positive. Now, if VBN is less than VDC by 2, which is possible, right? Because we know that VBN can be between 0 and VDC. So VBN, when the VBN is less than VDC by 2, our VBO becomes negative, which means now that we put a reference point in the middle of the DC link, the output voltage of the half bridge VBO can be positive and negative, right? So we can basically use this circuit, the second circuit, as an inverter, simple inverter, which is shown in here. So we just derived VBO is equal to VBN minus VDC by 2, and if we take basically the average, VBO average, so which will become because you remember we just write the formula before. VBN, the voltage in here, is basically MT times VDC. We derived it in our last lectures as well, and we saw it in the first slide. So if we replace that formula, replace that equation as VBN, we get this formula, and if you take the VDC out, which gives this, and because MT, which is our modulation signal, we know that modulation signal is limited between 0 and 1. If the MT is between 0 and 1, so VBO average, basically, if you put, for example, in this term, if you put MT is equal to minimum value 0, VBO average becomes minus VDC by 2, which gets the minimum value. If we put the MT as the maximum, which is 1, then VDC minus VDC by 2, which means plus VDC by 2. So by using the two extreme values of MT, we can get the two extreme values of VBO, which is the average of the output voltage for this circuit. And as you can see, the average of the output voltage is changing minus VDC by 2 to VDC by 2. Okay, so that's, by looking at both of these two slides, we can confirm confidently that this circuit, the second circuit, will give us a AC output voltage. So in that case, what we need to do, instead of connecting the grid, which is the grid, basically grid will have 2 points. Okay, one is the phase and another point. This is a phase and we call it a neutral. Instead of connecting the neutral of the grid to here, to the negative DC link, we need to connect the neutral of the link into the mid of the DC link. Okay, so which can give us fully controllable voltage source that can generate an average output voltage in the range of minus VDC by 2 and plus VDC by 2. But also we know that this is the average value, but because of the switching of the devices, there will also be a high frequency harmonics which we need to filter out from the system. So now how we do this modulation? Basically, the modulation will be exactly same as the half bridge, how you modulate the half bridge. So still you need to have this triangular wave, you still need to have the MT. The only thing is that the meaning of MT that will change, okay, when you go from this circuit to this circuit. How it will change is when we derived VBN, we considered MT as the percentage of the switching period when S1 is on, and when S1 is on, basically the output voltage was VBN was equal to VDC. Again, when S1 is on, this is like a short circuit, so VB is connected with the positive of the DC link, so the VBN is basically VDC. When the S1 is on, the output is VDC. When the S1 is off, its output is 0. So that's why we got this equation, the VBN average equal to M times MT times VDC, which we have derived in the past. Now, in this case, MT still means the percentage of switching period when S1 is on, but when S1 is on, basically VBO is plus VDC by 2, because yes, when S1 is on, this is still connected to the DC link, positive DC link, but now the voltage is with respect to this point. So that means when S1 is on, the VBO is plus VDC by 2, and when S1 is off, which means when S1 is off, my other device, the complementary device S2, this is on. This is on means this point is connected to the negative DC rail, and which means between VB and 0 we have this minus VDC by 2. So if we take the average of VBO, this we can write it because MT times VDC by 2, and MT is, you can assume it like a duty ratio. So there is a certain point, certain time, which is the on time of, we can say the on time of the top device S1, the voltage is VDC by 2, and the rest of the time, which is 1 minus duty or 1 minus MT, the voltage is minus VDC by 2. And if we take the average, we get the formula of this. Okay, so VBO average is MT minus half of VDC. Now, how can we derive a block diagram for the modulator based on this equation? So, what we'll do, as you can see, the block diagram for the half bridge modulator is slightly changed. Instead of, as you can see, we have this extra VDC by 2 term. So, how can we derive it? Just by looking at the earlier block diagram where we derived it. For example, if you look at the earlier block diagram, this block diagram here, you remember whatever voltage VBN we want at the output of the half bridge, we put it as a reference in here, VBN star. Then we divide it by VDC, which give us the MT. Okay. So because the circuit is still the same thing we can do in here. So here we can say this point the voltage is VBN star, and if you divide the VBN star with VDC, that will give you the MT. Then you compare MT with CT and to get the GB. Okay, but before VBN star, we need to use now, instead of VBN star, we have to use VBO star, because now that we are trying to get a voltage between B and this reference point. We are no longer trying to get a voltage between VB and VN. Okay, so that's why we need to use VBO star as our input to our PWM modulator block. Now, if you look at this formula, which we just derived, VBO is equal to VBN minus VDC. So, which means the VBN at this point is equal to VBO star plus VDC by 2. So, basically, with your input reference VBO star, you need to add the VDC divided by 2 to get the VBN star. Okay, so the only difference with the previous PWM modulator block is that, first thing, instead of using VBN star as a reference, you need to use VBO star as a reference. To accommodate this VBO star as a reference, you need to add the VBO star with the VDC by 2 to get the VBN star, and the rest of the stuff is exactly same as before. Okay. So if we write down, if we go back to the formula that we derived, so VBO average is MT minus half times VDC. So if we write it here, and if we do a rearrangement, we get the MT equation is this, and so basically, if you rearrange this, you get this equation, but instead of VBO, basically you will get VBO average T. Okay, and from this diagram, if you look at this part in here, basically here, if I write it down, first what you have is first you have the addition block. So for example, this block is just adding VBO star with VDC by 2, which is showing in here, VBO star plus VDC by 2. Then you divide it by 1 over divided by VDC, which you divided by VDC to get the MT. So from this block, we get so from this block diagram, we get this formula in here, and by using this equation, if we rearrange it, we get a similar formula, which means basically these two terms, the VBO star and VBO average, they are equal. Okay, so same hypothesis. In previously, when we, as I mentioned in our first slide, whatever VBN we want as the output of the half bridge, we put it as a reference in here as a VBN star. In this case, same thing. Whatever VBO average you want at the output of your inverter, you put it as a reference as VBO star. Okay, so that's what is showing. VBO average is equal to VBO star. So if you use this kind of PWM block, you can use the required output voltage, required AC output voltage as a reference to your PWM block, and that will give you the AC output accordingly if you use this PWM technique. Okay, so let's have a look at an example. So let's assume our input voltage is 600 volt. So that input DC link, the whole DC link voltage is 600 volt. So if we assume VDC by 2, so each of this voltage is 300, 300. And we have like a 1 millisecond. So basically the triangular waveform that you can see in here, the frequency of CT is 1 kilohertz. So let's assume from the inverter output, we want to generate 200 sine 2 pi 50t. So this is the voltage, this is the sinusoidal signal we want at the output of this inverter. So based on this formula, what will be the MT? So if you look at the MT equation, which I derived in here, from this you can see to calculate the MT, we have to, if you multiply 1 over VDC with VDC by 2, this term will become just half, which is 0.5, and VBO star divided by VDC. So basically, whatever voltage you have in here, you divide it with the DC link voltage, which is 600 volt, and the second term is half, which is 0.5. So by using the formula, we can get an expression of MT. So to achieve 200 sine of 2 pi 50t, to achieve this voltage, we need to use this function or this voltage as our MT, as our modulation signal, which you can see in here. So this is, first one is the triangular signal, the green one, which is the carrier signal, CT, and we compare it with the MT, which you just derived the equation, which is this. Then the GBT, as you can see in here, if you look carefully, the pulse width is changing, right? It's starting from small and gradually increasing, then again it becoming small, then again gradually increasing. So essentially, within the GBT, we have embedded our low frequency signal, which is MT. And once we look at the VBO, which is the output of the signal, and if you look at the red signal, which is the average of the PWM signal, which is the low frequency component of VBO, and if you look at the peak of it, as you can see, it's going to 200, right? And the frequency is, of course, still 50 hertz, okay? From here to here, if you look at the frequency, it's exactly same. So the frequency of MT and frequency of VBO average is exactly same. And as you can see, if we use this equation to calculate MT, we can achieve the right peak voltage. If we look at the peak, it's 200 volt. It's going from 200 plus to minus 200, which is, as you can see, the whatever output voltage we wanted, we are generating by using this circuitry. Is there any question on this slide? It's very important to understand. So basically, you start with the required output voltage, then use this formula that we derived in here to calculate the MT. And if you calculate the right formula of MT, if you put that value and use this PWM block, what you will see, the output voltage will still go from minus 300 to 300. So the green one is the voltage that you will see at the output. But if you take the average of the green signal, you will see this red signal is basically embedded within the green signal. Okay? Or if you take an FFT, the green signal that you're seeing, the pulsating VBO, if you take the FFT of this signal, you will see that at 50 hertz, you have this, this low frequency component. Okay? So if we do the average, if you do the equivalent circuit, what we can write, same as all the other half bridge inverter or half bridge circuits, we have a variable DC link, a variable output voltage, as you can see in here, plus a high frequency. And this high frequency one, of course, we don't need it. We can filter out by using an inductor in here. But the important thing is that we are generating now a fully controllable voltage in the range of plus minus VDC by 2. Okay, and this pulsating voltage, which is changing from VDC by 2, will have the pulse width, which is changing. Again, if you look at here, see, gradually the pulse width is increasing and decreasing, which showing that the low frequency signal is actually embedded within the pulse strain that is generated by this inverter circuit. And we just want to get rid of this high frequency component by using a filter. Now, although we have done this analysis for this full bridge in the inverter using not a full bridge but just a half bridge, But this is not really common. Yes, you can generate an AC signal, you can generate DC to AC, but it's not a common solution. Why? First thing is that sometimes it's challenging to get a DC link midpoint. Okay. Another thing is that it's not all that this kind of connection can cause unbalanced, DC link. So if you look at the circuit, depending on what sort of current you inject in here, because this is in the middle of the DC link, if depending on the current injection and the current path, the two voltages which we need to be equal, we need VDC plus 2 and VDC plus 2 and VDC plus 2 for both top and bottom sources. But depending on the current flowing in the circuit, there could be imbalance, because you will see normally we stabilize this DC link with using capacitor, and the capacitor charges discharges, as depending on what sort of current you are injecting here, there could be imbalance, and that can cause problem. The most obvious reason is that maximum AC voltage we can generate is only half of the DC link. Okay, so even if you have a 600 volt DC link, as you can see, our DC link total voltage was 600. But if you look at the plus and minus of the output voltage, it's only going from 300 to minus 300. So basically, you're not utilizing the full of the DC link. So, which means to generate a 200 volt peak, we have to use a 600 volt DC link. So the generated output voltage is, so we have to use 3 times the peak of the generated voltage as the DC link. So you understand, so the margin is really big. So you are trying to generate a 200 volt peak AC signal, but to do that you have to use a 600 volt DC link. The reason is we are not utilizing the DC link properly in this circuit. So, which is led to the introduction of the full bridge inverter, and basically it's as simple as connecting 2 half bridges together. So you have, as you can see, you have 1 half bridge in here, another half bridge in here, and then you control the basically 2 half bridges with the 2 PWM modulators that we saw in here. So this kind of 2 modulators. For each of the half bridge, we'll use each one modulator like this one, and then we will be able to generate a nice AC output as the output of this full bridge inverter. This slide, from this slide, the analysis of the full bridge inverter we'll look at tomorrow. Okay? So that's it for today. Thank you.